Sometimes it's fun to try to figure out the next number in a series based on what's already there. Unless what's already there happens to be the first part of my phone number, which this is. In that case, it's a little hard to predict. Because in order to predict the next numbers, we have to find some kind of a mathematical pattern in the whole series, like what we see here. Each pattern has a rule or formula. That's what makes it a pattern instead of something random like a phone number. Here, the first list has the rule, add 3. The second, multiply by 3. The third, well, you can see it for yourself. Lists of numbers like these with a particular order are called sequences and are written with variables and subscripts. The subscripts are used as labels to point out each position in the sequence. Every sequence has a rule. We can turn that rule into a formula that describes the whole sequence. It looks a whole lot like function notation, and it is. We can substitute specific whole numbers into the formula, and the formula will crank out the appropriate number answer. How many different kinds of sequence are there? Think about it. You could probably invent a few hundred different formulas right now without even breathing hard. And as long as you or anyone keeps writing formulas, there will be more and more different kinds of sequences. Ultimately, the number of possibilities is infinite. But we're going to concentrate on just 2 of them. The first is called an arithmetic sequence. In this first type, you get from each term to the next by adding the same number. A moment ago, we saw the sequence 1, 4, 7, 10. We took each number and added 3 to get to the next one. That number that you add each time is called the common difference, D, and we can use it to write down this all-purpose formula for arithmetic sequences. If you know any term of the sequence, this lets you find the next one. The sequence we just saw, for example, would look like this when we apply the formula using the common difference of 3. Great, but what if someone asks me for the 10th term of the sequence? I can't tell them unless I already know the first 9. Let's see if we can do something about that. Look at our numbers again and see if you can spot the pattern. What will the formula for AN look like? The formula comes out looking like this. The first term plus the right number of copies of D. How many copies of D? N minus 1. This new formula, together with our earlier formula, will answer most questions about arithmetic sequences. Here's one to try. Use the pattern given to find the first term and difference. Then use our new formula to find the 100th term. The formula appears here at the bottom. Well, the first term is easy. That's 3. I subtract 2 terms to find the difference, which turns out to be 5. I know it's an arithmetic sequence because all the differences are the same, 5. So I can calculate the 100th term easily by using the formula. Since n is 100, n minus 1 is 99. And the formula tells me that what I'm looking for is A1, or 3, plus 99 times D, or 99 times 5. My answer, 498. The second kind of sequence is geometric. The difference is that in arithmetic sequences we added. In geometric sequences, we multiply. The pattern comes from multiplying each term to get the next term in the sequence. You can see it at work here. So what we need are formulas, 2 of them, to match the 2 formulas we just produced for arithmetic sequences. The first formula, what's it going to look like? Geometric sequence, multiplication. This time we get from each term to the next by multiplying by the same number each time. That same number is called the common ratio. That's simple enough. Now what about the other formula? How are we going to find the 100th term without writing down the other 99 first? Look closely. You see a familiar relationship, but this time it shows up in the exponents. And the second formula takes the form you see at top here. Together, these 2 formulas make geometric sequences work. Now get ready to use the formulas to find the answer to this question. A13 equals what? Start by finding the value of the first term and the common ratio. Take it from there, find the answer, and come back. As always, the first term is easy to find. I simply read it. 4. The ratio is 1/2, because that's what I multiply each term by to get the next term. I substitute in the formula and find that A13 is going to be 1 over 2 to the 10th. The next trick to learn is what happens when we add up the terms in a sequence. The first thing that happens is that we get a new name, series. When the list is all in separate pieces, separate numbers, it's a sequence. When all those numbers are added together, it's a series. As a series, it has its own special notation. The big letter, sigma, is just a capital S in Greek, and it stands for sum. K keeps track of your label, your position in the series, and tells you to start at 1 and keep going until infinity, forever, in this case. Now we're going to get formulas for sums or series, just the way we did for sequences. Here's one small part of the arithmetic sequence we had before. We've turned the sequence, the list, into a series by adding, and we want to know the sum of the first 5 terms. The first thing we do is write the series down twice, once forwards and once backwards, and then stare at it closely. And immediately we see a very interesting pattern. Each pair of numbers adds up to 14. But notice what that means. The two series contain the same numbers, once forwards and once backwards, so each complete series adds up to 1/2 of the total sum. And the total sum? Obviously, it's 5 times 14. You can see it right here. So the first series, the one we're trying to add up, equals exactly 1/2 of 5 times 14, and we've found our answer. And we've found the answer to your next question as well. The question goes like this. Why didn't we just add 1 plus 4 plus 7 plus 10 plus 13? It's easier. Let's answer that question with a question. What if we're looking for the answer to this bottom problem instead? All the terms of the sequence until you get to the 103rd one, which happens to be 307. Maybe you'd like to add up all of those without making a mistake, of course. I'd prefer to use our little trick. Add the first and last terms, multiply by the 103 copies that we have, and then divide by 2. What we've done, of course, is to create a general formula for finding the sum of an arithmetic series. It looks like this. The first two symbols, the one using sigma and the other using s, both stand for the sum of the first n terms of the series. And the last line describes the formula we just worked out. You might suspect that there should be a somewhat different formula for a geometric series. And there is. It looks like this, similar to but different from the formula we've just been looking at. But if we know how to use that one, we should be able to figure out how to use this one too. So take a close look, and then we'll try it out on this problem. First, we have to recognize all the parts. The first term is 8. The common ratio is 1/2. Each term multiplied by 1/2 gives us the next term in line. We need to know how many terms we have that we want to add. You can figure that out by counting or by using your formula for the nth term. Watch out for those exponents of 2. And that provides us with all the ingredients for the series formula. So we substitute our numbers in the formula, and we get something that looks like this. You can work it out on your calculator if you like and see if your calculator agrees with mine. So that question turned out to be fairly easy. Here's a tougher one. What happens if we just keep adding terms forever? Do we get an answer? Or does it go on growing forever? We can answer that by taking a very close look at our sum formula. We notice that the only thing that changes is r to the n. If r, the common ratio, is 1/2, as it was in the problem we just looked at, then r to the n will get closer and closer to 0. That happens as long as r is between plus and minus 1. And it gives us this formula for the sum of infinitely many terms. Apply this formula to the series we saw earlier, and what do we get? We get a sum of 16 for the whole infinite series. Now that would be a little difficult to do without the formula. We'd have to go on adding by hand forever. Before you go, take another look at the two formulas which are crucial for the handling of arithmetic sequences and series. And the other three which play exactly the same role for geometric sequences and series. Check your textbook for more information and find yourself some problems to do for practice. Good luck.